In this video, we will explore the concept of a singly linked list. We will cover the introduction, insertion, deletion, and traversal aspects of a singly linked list. Let's get started. Let's delve into the structure of a node within a singly linked list. Here's a Python implementation of a node class. The class node has a constructor which takes data as argument. Inside the constructor, first the data is stored inside self.data. This is where the actual value of the element is stored. Second, self.next is assigned none. This is the reference to the next node in the list, and it's initialized to none, meaning it doesn't point to any node initially. Below this, we are creating nodes. We create a node named head with data 10. Similarly, we create another node named second with data 20 and third node with data 30. Finally, we link these nodes together. Head.next is assigned second, meaning the next pointer of head now points to the second node. Similarly, second.next is assigned third. That means the next pointer of second node points to the third node. Each node in a singly linked list contains a data field to store the element's value and a next pointer that references the next node in the sequence. The next pointer of the last node contains none, indicating the end of the list. In the diagram, the data field stores the value 10, and the next pointer points to the next node. This is how individual nodes are structured and connected in a singly linked list. Now let's see how to initialize a linked list. Here's the code for the same. A linked list class typically contains a head pointer that points to the first node and methods to insert, delete, and traverse nodes. Initially, the list is empty with head equal to none. Below this, a new empty linked list is created by calling the linked list constructor. In the diagram, we can see that initially the linked list is empty. Therefore, the head pointer points to none, indicating an empty list. Let's discuss the process of inserting a node at the beginning of a singly linked list. Here is the code for the same. The insert at beginning function takes data as argument. First, a new node is created using the data. Second, the next of the new node is assigned head. This points the new node's next pointer to the current head of the list. Finally, the head is assigned new node, updating the head to point to the new node, making it the first node in the list. Let's summarize the steps. First, create a new node with the given data. Second, point the new node's next pointer to the current head. Third, update the head to point to the new node. Initially, the head points to the first node having value 20. Now we create a new node with value 10. We point the next of new node to current head. Finally, we update the head pointer to point to the new node. Now let's see how to insert a node at the end of a linked list. Here's the code for the insert at end function, which takes data as argument. First, a new node is created with the given data. Second, we check if the linked list is empty by checking if the head is none. If the head is none, then we assign head to new node and return. Otherwise, we traverse to the last node of the linked list. We start from head and iterate until last.next is not none. Finally, the next pointer of last node is updated to point to the new node, effectively adding the new node to the end of the list. Let's look at the steps visually. First, create a new node with the given data. Second, if the list is empty, make the new node the head. Third, otherwise, traverse to find the last node. Fourth, update the last node's next pointer to the new node. Initially, the head points to the first node and the second node is the last node. To insert a new node at the end, we traverse to the last node and update its next pointer to the new node. Let's learn how to insert a new node after a given node in a linked list. Here's the code for the insert after function, which takes previous node and data as arguments. First, we check if the previous node exists. If the previous node is none, then we print an error message. Otherwise, we proceed to create a new node with the given data. Then the next of the new node is assigned previous node's next. After that, the previous node's next is updated to point to the new node, effectively inserting the new node after the specified previous node. Let's see the visual representation of the steps. First, check if the previous node exists. Second, create a new node with the given data. Third, make next of new node as next of previous node. Fourth, make next of previous node as new node. Let's consider an example where we want to insert a new node with value 25 after the node with value 20. In step 3, the new node's next pointer points to the third node having value 30. In step 4, the second node's next pointer points to the new node. Now let's learn about deletion in a singly linked list. Here's the code for the delete node function, which takes key as argument. First, we store the head node in a temporary variable. Second, if the head node has the key to be deleted, then we update the head to the next of head node and return. Otherwise, we search for the key to be deleted. While searching, if the next node contains the key, then we update the next pointer of current node to skip the node to be deleted. First, if the head node contains the key, then we update the head to point to the next of head node. Second, otherwise, find the node before the one to be deleted. Third, update the next pointer to skip the node to be deleted. In the top diagram, the head node contains the key to be deleted. Therefore, the head node is updated to point to the next of head. In the bottom diagram, the second node contains the key to be deleted. Therefore, the next pointer of the first node is updated to point to the third node, skipping the second node. Now let's see how to traverse a linked list. Here's the code for the print list function. First, the temp variable is initialized to point to the head of the linked list. Then we traverse the list until temp becomes none. While traversing, we print the data of current node and move to the next node. Finally, we print none to indicate the end of the list. Traversal is the process of visiting each node in the linked list exactly once, and it is used for printing all elements, searching for a value, counting nodes, and computing aggregate values like sum or maximum. In the diagram, the traversal process is shown. The variable temp initially points to head. Then, it moves from one node to another until it becomes none. The output of the print list function is 10, 20, 30, and none. Let's see how to search for an element in a linked list. Here's the code for the search function. First, the current variable is initialized to point to the head of the linked list. Then we traverse the list until current becomes none. While traversing, we compare the data of current node with the given key. If the key is found, then we return true. Otherwise, we move to the next node. If the key is not found after traversing the entire list, then we return false. In the diagram, the search operation is indicated with the circle. The function searches for the key 20 in the list. The key is found in the second node. Therefore, the function returns true. Here's the performance of linked list operations. Insertion at the beginning takes order of 1 time. Insertion at the end takes order of n time. Deletion takes order of n time. Finally, searching takes order of n time. All the operations take order of 1 space. Let's summarize what we have learned so far. A singly linked list is a linear data structure with nodes containing data, and a reference to the next node. The first node is called the head and the last node points to null. Basic operations include insertion, deletion, and traversal. Insertions at the beginning take order of 1 time, while other operations typically take order of n time. Linked lists are dynamic and can grow or shrink at runtime. Unlike arrays, linked lists do not require contiguous memory allocation. Some of the common use cases of linked list are implementation of stacks and queues, undo functionality, hash tables for collision handling, memory management, and graph adjacency lists. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.